Okay, thank you. Good morning, everyone. Really sorry I can't be there. I'm quite sure it's more my loss than it is yours. Had a clashing meeting here at ESTech. So I was asked to give a presentation on cross-calibration activities for radiation monitors. Just a couple of words beforehand. I mean, here we're really talking about monitors, not science class instruments. And some work we've been doing over a decade with GOES instruments, as well as a view with what's coming with our monitor instruments and how they might be leveraged to make use of. So this is a overview of my my presentation. So first, I'll talk about the SEPM reference dataset version 3, including the high energy extension, which has been worked on by several people in the meeting and in the consortium. Then I'll mention. Is there a problem? No, it's okay. Or
yeah,
Thanasis, you trying to say something? I'm
no,
not hearing you.
For us here and online for George seems okay. I don't know what the problem is.
Okay, I just heard some feedback or something coming through. So okay, never mind. I will continue.
Okay.
Just wave your hands wildly or scream if something goes wrong. And then talk a little bit about a lunar gateway and why that could be relevant for extracting a little bit more value out of these data. So this is an overview of the GOES instruments. Now GOES is the backbone of what we call the SEPM reference data set, which is a long-term data set going back to the 70s up until 2017, which we used initially for specification modeling. That's its main purpose. We know people are trying to use it for more space weather, and I'm very scared to say space science, but okay, if they want to, they can. They have to understand some of the caveats that go on, and here I'll touch upon some of those. So the primary reference data instrument is SEM, which includes EPED, which is the medium energy detector, and HEPAD, which is the Cherenkov detector. And we're using data from GOES 5 to GOES 15. And also earlier there was SMS data, which is incorporated in the reference data set, but I won't speak more about that. So here on the bottom left, you can see the EP detector. And if I could find a marker, that'd be great. Let me see.
We can't hear you very well.
Okay, never mind. Are you okay now?
Yeah, we can hear you now. Yes.
Okay, sorry. So bottom left, you have the SEM detectors made up of a telescope and 3 dome type detectors, which you can see here. They're very simple. They have a couple of detectors behind, and on top they have varying different thicknesses. And then you have the telescope detector, which is has this little hole here, and then some detectors below it. And then here you see the Cherenkov detector with the radiator and the photomultiplier tube. And here are some of the responses. So the reference data set version 3 is the one we are releasing now. We've been trying to release it for a year or so, but because of backlog in our project, it's taken a bit longer, and we wanted to also get it right. So version 3.0 is really just the cleaned data, so the removal of the fluxes, and then we stamp this with what we call the effective energies. And if you're probably familiar with the work from Ingmar and geophysics research letters from 2014, effectively what it means is we take IMPATE GME data and we see which of the channels, interpolated GME channels, most closely represents each GOES channel, and we assign the GOES channel that energy. Version 3.1, then what we want to do is extract what we call the signal. So that's not the GCRs, but the SCP signal. And again, Ingmar has developed a method for doing this. It relates to a background level, but it's also a statistical significance of what we're seeing above that background level. And on the basis of this, we have a background subtracted data set, but it's still at the in the channels that we received the data originally. So here you can see the before and after image for one HEPAD channel. The reference dataset version 3.2 is where we now join everything together. So we have the effective energies that we stamped on the beginning, and we now link it all together so we interpolate to the same energies. And that's because for each, even though the GOES instruments are nominally the same, they're not actually the same. And so we get some differences in the effective energies, and this will remove that. Now I'm going to talk a little bit about HEPAD later, because as this meeting was starting, I noticed there was a lot more focus on this. But effectively for now, we're using the P9 and P10 channels. And if you look at the appendix of Oscar Raukkonen's paper from 2018, in which he presents the bow tie analysis from Juan Rodriguez that Ingmar mentioned the other day, that's basically what we're using. We've tried a lot of other approaches to eke out a bit more of that data, but there are problems. And I'll mention those in the next slides. Version 3, I genuinely think this will be available in July to the public. So because I've seen the finalized data set, we're just cleaning up some bits and pieces now. But just to give you an overview of how it looks, what our approach is, we want to give all the different levels of the data, so that if you say, I don't trust your processing at this level or that level, then you can do it yourself. But basically 3.0 will be files per species, instrument and spacecraft. So we just group SMS 1 and 2 and GOES 1 and 2, but the rest are all independent. Of course, HEPAD is only available from 1983 onwards. Then for 3.1, we have files per species, spacecraft at low energy and at high energy. So that means that we're merging the HEPAD and the EPED data sets. And here we're not issuing data that overlaps. So we've already selected which data sets we trust the most, and the data set will end where in 3.2 we're not going to use it anymore. The 3.2 then is just files per species, so you'll just get protons and alphas. And yeah, it's a contiguous time series going all the way from 1973, is it, or 1974, I think, up until the end of 2017. The data is interpolated to the energy channels that we use, is extrapolated using HEPAD where we have it. Actually, for the earlier data, we've used another extrapolation regime that I derived, so that you actually get the high energies even for the earlier data. And we've done a test with that when we apply it to the later data where we really have HEPAD data to verify it. We can then derive integral channels for all of the protons. For helium, Shabas has derived a method for deriving the higher energies. Ingmar mentioned this as well the other day a bit, and then we can derive helium integral channels as well. And it is our intention to make the radiation geometry models available. So I'm going to speak a little bit about that in the next slide. So the thing we wanted to do as a kind of 3.3 was a kind of more space weather version of the data set, where we get rid of this contamination that you see in the early events in GOES, and to be completely fair, you see it in the early parts of events for many radiation monitors. In GOES, it's quite simple to understand what's going on. Effectively, you have a very small pinhole here at the top, and then you have a couple of detectors below. And if a particle has enough energy, it will penetrate through the shielding and impact the detector, get slow through the shielding, and look like a low energy particle as it impacts here. And we've simulated this in GM4, and you can see in this response function here, so we have just channel 2 and channel 3, we have this outer band response in the channel 5 region. and that is as a result of this these normally incident particles. We have also something coming in channel 6, which is more a slant angle, which is present there. We tried a couple of methods to correct for this. I should just say in the bottom, yes, this is where you can see the contamination very clearly. This is just looking at times when these low energy particles shouldn't be able to arrive. And we have very, very, very strong correlation between channels 2 and 3 and the higher energy channels 5, 6, and 7. So we tried to sort of correct this analytically just by doing a multi-parameter regression, where we can see we can get some correction. This is when the channel 3 photons should be able to arrive, and this is when they do arrive, and we're trying to sort of get rid of this. And you can see it sort of works, but it's nowhere near good enough for a kind of public release of a data set. The other thing we tried then is to use the response directly. So if we have the data from the high energy channels, we can fold that with these response, subtract those counts out. And that's what you're seeing here. The purple line is really the reconstructed contaminated count rates. And that's a bit more promising, but it still didn't really reach the level we would need to have a version 3.3 of the data set. But like I said, we want if people want this model and the response function analysis we've done, then we're willing to distribute that if people want to work more on it. Otherwise, one needs to consider that at the onset of events, you shouldn't trust the lower energy channels because of this clear contamination effect. So now I want to talk about HEPAD very briefly and the problems therein. So here you can see the responses for HEPAD for the earlier GOES and the later GOES. There were only 2 instruments tested at Brookhaven, but this is representative of GOES up to 6, and this is from 8 onwards. GOES 7, the HEPAD was not working or used. So what you can see here is if we just use the 2 channels 9 and 10, which are these ones here, and we try to reconstruct the count rates based on a spectral form that we throw at it. So we optimize that spectral form, and we see we optimize the fitting of the spectral form. So we select the best spectral form to reconstruct the counts. And what you can see here is we get a very good agreement with the bow tie energies for these that were produced by Juan Rodriguez and published in that paper from Moscow. So that's pretty nice. But the problem is that we have 2 other channels which don't agree at all. And probably the reason for that is because once you consider the rear entering particles from channel 8 and channel 11 is an integral channel in any case, then you see this kind of long tail, and it's difficult to correct that. But if we try, and here I've used a exponential cutoff power law distribution, but I'm doing it every time step, by the way. So each data point is reconstructed per time step, which is why you see funny business down here when we get down to background level. We can reconstruct a spectrum. This is the fluent spectrum of the event, and that's quite encouraging. So you could say we could reconstruct all the counts simultaneously, but in reality, we have some relatively significant errors, and it's probable that what's going on is that these response functions, you can see this is nominally the same instrument, but these response functions, even the interpolation that we're doing here is probably bringing in some significant error, and there might even be some other factors that are not really considered within this. So that's something that I think would be interesting to revisit, actually, the simulate the response functions of GOES, because we have the geometries, and I think now we have the tools in GN4 to do this. This is an error analysis. So I did a lot of different types of fits, and you can see that the best is for the 4 channel, but this is the errors considering all of the different channels. So okay, where we're trying to fit all of them, we probably should get a better result. And then finally, I think this is interesting. So for the 4 channel fit, what you can see here is the power law index, the scaling factor, and the cutoff energy. So these are the 3 parameters you see in an exponential cutoff power law. And the power law index, you should read it. This is less negative at the bottom. So this is -2 and this is -9. So the lower this value is, the harder the spectrum. And when you see the injection initially, you see a very hard spectrum, and it softens, and then you get the ESP event. and then later when you get more injections, it gets harder and then softens again. So basically this seems to work, but this is for October 1989, and it's the best case we have. So there's certainly some tweaking that could be done, but I still think that we have an issue in the responses that needs to be revisited to make this useful. I just added those slides in because I thought it seemed, in the context of this project, the kind of stuff that you guys were really interested in looking at. So the second topic I wanted to talk about was our radiation monitors. And I should say here, there are some that are really basic monitors, and there are some here that are getting towards science class instruments. But just to give an overview here, SRAM's been flying for a long time on various different missions. Proba 1 is still flying, Integral is still flying, Planck and Herschel, those missions ended. So we have quite long data sets there. I think that the Ingmar and then Shabazz at Spark have done a lot of work to try and get more and more of the value out of this data. More recently, we've had the next generation radiation monitor, and this instrument is flying on EDRSC, has been for about 5 years, and Sentinel-6 for about 4 years or 3.5 years. And it's also flying now on METOP third generation, Meteosat third generation, and it will fly on METOP second generation. That Meteosat third generation, they had a bit of a problem with the feed, but I think that data is coming. I'm not going to speak too much about Gateway on this slide because I'll speak about it later. EMU on Galileo, it's a very useful electron measurement, especially, but the proton measurement is also quite useful. We've got RADAM going to Jupiter on JUICE, and various other instruments here that we are developing that are either flying or are going to fly soon, such as Proba 3 should launch this year with 3D EES. That should give us some 3D distributions, and Norm as well should fly on this HEO type orbit in the northern latitudes. One thing I want to mention is HEPI, which is high energy proton instrument. So this is going to be a Cherenkov type detector that we're developing with the University of Surrey. And as part of this, we've developed some more GN4 tools for simulation of the Cherenkov detector with the silicon proton multiplier. Those could be brought to bear with EPAD, as I mentioned before. But hopefully we can get an IOD flight for this in the short term, and then we can actually start producing Cherenkov detectors for space weather in Europe, which I think would be very beneficial to many users. Very quickly on SMRM data. Okay, I will probably pass by this slide super quickly then, because there's some more things I want to say. But this is just an example of some of the work we've been doing in the G6 context with SRAM data, and here you can see EPT data. The next slide have an overview of the NGM data. So in the top part, you can see the electron responses, the electron count rates with the EOR phase for EDSC. And then this is the recent event as measured by Sentinel-6 for the electrons. So you can see the injection increase in the belts. And then the same here for the proton detector, so proton responses, the EOR phase for EDRSC, and then what we saw in Sentinel recently with an enhancement here of the inner belts, which is probably some SCP trapping, and then getting radially accelerated inwards. So the last thing I wanted to talk about was contributions to Gateway, and the reason I want to talk about it is because we have this payload called ERSA, European Radiation Sensor Array, and on that we'll have SRAM, NGM, and ICAR-NG, as well as some pixelated detectors like HardPix and MAGIC for magnetometer. It's going to be a big challenge to get useful magnetic field data out of it, but maybe coarsely we can get some information on the direction. And what this is going to let us do is, for the first time, to cross-calibrate and create unified data sets for these instruments, and then go back over all of the previous flight heritage and see where we might have been going wrong. And that should allow us to bring the level of data closer to science data. So I think that's very that should be a very interesting flight. I mean, it was really an opportunistic thing that ESA jumped on when this mass became available for a payload. I think if we knew now what we knew then, sorry, if we knew then what you knew now, that we had more time, we could have done a more proper call and had more science instruments. But we thought it was going to be launching this year, and it's not launching this year. This is the last slide I have, Thanasis, so I hope I'm not overrunning too much. This is the orbit as modeled for ESA on the first elements of Gateway. These are some intentions we have for the radiation monitor cross calibration, and then we want to use this as a kind of prototype service for radiation protection. Those are important things that we are working on with new activities coming out to cover those in the next months. And lastly, we did a study using SRAM data for the solar electrons, which we'd not really looked at before. And SRAM basically gives you two types of channels. They give you pure proton channels and channels that are electrons contaminated with protons. Let's put it like that. So we didn't know if we could really extract any useful electron signal, but certainly in the onset of events, we can extract useful electron signal, which could be used for forecasting. So that's very useful. And as I said, when we have these instruments combined together and we have more detectors, we're optimistic that we can extract a more pure electron spectral information. And I think with that, I've probably taken at least 3 minutes since you said, so I will stop there. Thank you.
Thank you very much, Piers. Let's thank our speaker. Any questions, comments? Rami.
Hi, Piers. Thanks. What are the plans for releasing these datasets?
Which datasets are you speaking about? The ESA ones?
Yeah.
So the plan is quite clear. Actually, they should be released as close to real time as possible, but not less than 6 months from when they're measured. Right. So I can give you some vision of how I see this because I'm now acting as the project scientist for ESA. How I see it is that the EOR phase, which is going to take 450 days, in that part we're going to do some scientific investigation on the measurements we're seeing in the belts, and as we do that, we'll verify the algorithms to get the unified data sets, such that once we're on station, we can really release them, what we're calling level 2, level 3 data per instrument, and also in a unified sense in close to real time. So I'm very hopeful, although I can't fully commit to it. I mean, the level 1B data, which is what we call the first count rate data, which is not science data, that has to be in near real time anyway. But I'm also quite confident that the level 2 and 3 data and this unified data set should also be in real time once we're on station, which you can anticipate being something like 2029. And then you're measuring SEPs.
Okay, thanks.
Yeah, it's Bernd here. I always have the question, why is on these very perfect missions not a science-driven radiation detector on board? I mean, you put in all of this radiation monitors. In total, you have whatever tons of spacecraft, and you're not allowing a 5-kilogram science instrument aboard. Why is this the case? Why are you not putting in? I mean, we need to degrade our EFIN in order to get close to what SRAM is doing. So why is that not the case? I mean, I'm talking now for ages on this.
No, I fully understand. And so this opportunity, when it came up, was something where we understood we had next to no time to put a payload together, and we just had to use things we had off the shelf. At the time, I think you mentioned to me that there was even the flight spare of Solar Orbiter HET, I think it was, available, which we didn't know. And honestly, for full disclosure, I was not involved in this process at the time. But we're now looking to launch in the next years, but we were really meant to launch this year. and they just said we need to go with something as soon as possible. However, so that's kind of clear mitigation that I'm giving there. As I say, I wasn't directly involved with the selection at the time. Obviously, for us, it's also good to have this opportunity for the monitors. But if we think about the future, there should be a follow-on to ESA, so-called ESA 2.0, and then we will do it the proper way, as in we will get the requirements of the measurements that we need to make. We will see the instruments that fulfill those requirements, and we will launch instruments that should be of more science quality, such that we can measure those at Gateway. And that's why I've tried to be careful to say in my presentation here that we want to build a kind of prototype service. I'm hopeful that in the future we will have a more reliable service, but that should be based on more high fidelity data. So I know it's not a fantastic answer. It's an honest answer, and I hope you can at least appreciate that.
Okay. So thank you very much, Piers. We have to stop at this point. Let's thank our speaker.